Thin film resistance. Here we have the conducting film of all thin plate. Two terminals are connected to the plate. Our task is to calculate electrical resistance. I'm going to repeat the real experiment. I will use QuickField simulation software to run a virtual experiment. The conducting plate is thin, so I'm going to use a two-dimensional analysis. In the geometry model, I will draw a plate, specify electrical conductivity, and connect the voltage source to the terminals. QuickField will calculate the current density distribution and will be able to measure the current. The resistance is the ratio of the applied electric potential to the current value. There is an analytical solution here, so I will be able to verify the simulation results. Okay, let's start QuickField now. In QuickField, I create new problem. Conductor. Next. Problem type is DC conduction. The plate thickness is 1 mm. Model class is plane parallel. Length units are millimeters. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. You should draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. The model is simple, so I'm going to draw it here from scratch. First, I'm going to insert a rectangle with the dimensions of 26 by 6 millimeters, and the insert point will be this one. Close, zoom to fit. Next, I switch to insert mode and add the vertex here. You can see the coordinates here at the right bottom corner, 6 millimeters to the right. Okay, that's the geometry model. This is the plate, this is one electrode, this is another electrode. Let's assign labels. Through labels you can provide material properties and distinguish geometric objects. Switch to select objects mode, click the object to select, and here in the properties I specify a label for this block, conductor. Click this edge, and for this edge I specify a label electrode. Let it be grounded electrode 0. And this would be the electrode with some electric voltage applied. Now let's provide physical properties for these labels. Double-click the label name in the tree. Electrical conductivity of the conductor is 10 megasiemens per meter, so 10 E6, 10 millions. Okay. The grounded electrode electric potential is 0, and the electrode with some electric potential applied is 1 millivolt. Okay. Now the geometry model and the material properties are ready. And before I can run the analysis, I should build the finite element mesh. Just press this button, the mesh will be generated. Now you can solve the problem. Save all problem files. Let's take a look at the results. Here you can see the current density distribution. And you may note these sharp corners. They look unnatural. Let's use solve and refine option and calculate more accurate result. Just click OK. The finite element mesh will be adjusted. The problem will be solved again, and you can take a look at new results. It is better now, but let's do solve and refine again. Okay, that's enough. Now what we have here, you can see the current density color map. You can adjust the field picture and switch to electric potential color map. You can also switch on the vectors and see the current paths Let's change the presentation value to current. Scale factor 10. You see the current density distribution is not uniform, and I can use the contour tool to calculate the current. Just click the electrode, open the integral calculator, and here is the current value. Let's put it here. Now let's measure the current on this electrode. The values should be the same. Contour, remove contour, click this electrode, contour, change direction. Now you see there is the difference between this value and this value. So you can guess the accuracy of your results. In fact, both values should be the same, and the error is caused by this place. Let's again switch on the color map of the current density. You see, in this place, the current density tends to be infinitely large, and that caused the calculation error. You can get more accurate results if you build the contour avoiding this area. For example, contour, remove contour, contour. The contour you can plot in any place, just to make sure that the contour crosses all the current paths. This would be a nice contour to measure the current. Integrals 2.6. The sign depends on the contour direction. If the current comes from the right side, it is negative value. I can change the contour direction. Now the current comes from the left side and it is positive direction. The magnitude is the same. Now you see the difference is quite small, less than 0.5%. But my task not only to measure the current, but also to calculate the resistance. And the resistance is the ratio of the potential difference. Remember, we have specified the potential difference of 1 millivolts to the current value, 2.63. Let's calculate the result. Paste it here. 3.8 times 10 to the power of minus 4. 3.80 times 10 to the power of minus 4 ohm. There is an analytical solution to this problem. I can use this equation. G is 20 millimeters, H is 6 millimeters, conductivity is 10 megasiemens per meter, 10 millions. And this is thickness of the plate, which is 1 millimeter. I should convert to meters. Now let's calculate this value. 3.80 times 10 to the power of minus 4. That was calculated in QuickField, and this is the analytical equation. We have the pretty matching results here. Okay, what else can we calculate here? I can use the contour tool to select the entire plate, and for this plate I can calculate the joule heating. That's the value. So this way you can use QuickField simulation software to perform virtual experiments. If you search for the thin film resistance on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free,